So I'm a faculty member at Utah State University, very close to Idaho. So I'm super happy that you're hosting the workshop, and thank you for the 10 minutes to tell you about some of my work. So what I want to argue today is that we can fully solve now and successfully do very high numerical precisions in dynamical general relativity. But I will argue that sometimes we can still use some other proxies to visualize some of the aspects of black holes. And in particular, what you see here on the right are the shadows of certain black holes, and in particular binary black holes. So what I am going to argue is that there are some proxies, some analytical solutions, and then some numerical Python ray tracing, backwards ray tracing methods that one has to use, and we developed to emulate what you can see in these images here, and obviously not the full, disk and all the brightness and fully disks and different things in here, but just the shadows of the black holes with some proxies. So the three things I want to show today is these three images in here. And for that, I will use something called the black hole shadows that you all know what they sort of are. Some new things that are called Weyl coordinates. And I will present to you some binary black hole solutions of general relativity that can emulate and capture these images of the shadows in a proxy way. So as we know, we have the sun's and light, and we have the black hole. The black hole bends the light rays, and so we can kind of now know where we can trace the objects. And in particular, to emulate the shadows or to look at the shadows of black holes, we need to build an image of the event horizons that are lensed by that black hole. We've studied very well the Kerr black hole. And so then the question was, can we determine those shadows that are dependent not really on the geometry itself, but the photon orbits within that background that emulate binary black holes, and what do we get by doing so? So how sensitive in some sense are these shadows to the details of the horizon geometry? And here comes the Weyl geometry or coordinates that I was referring to. So there is some corner of analytical solutions that are written in this Weyl coordinates. So you can go smoothly from your typical Bouillard-Lindquist coordinates TR theta phi to this raw C T phi and write all solutions that you know, the stationary axisymmetric solutions, Schwarzschild, Kerr, everything that you want in these coordinates. But we were also very lucky that we found a way, not myself, others, of writing solutions that contain a binary black hole system. And those are exact solutions of a general vacuum, general relativity. The issue is, and you see here represented, is these two rods in these coordinates. The black holes are just some rods, but in between there's a mathematical construction that doesn't carry any mass. It's called a strut that realizes the effect of, because the binary system is not accelerated, it's not rotating, yes, it's static in there, that prevents the collapse from the self-gravitational effects. So what we wanted to construct is what are the shadows of these systems that have and are asymptotically flat, they're smooth everywhere, but for this line between the two black holes. And so we did that. We put some flat space-time behind us, and we ray traced back and constructed some Python methods to solve the light rays. And so what happens is on the left, you see what you would see without the black hole, and between us, the observers, and that image of the flat space, if I put the black hole, then the image is lensed. So here there are two images. There's the shadow, the edge of those photon orbits that are the ones that correspond to the shadow, and on top of that there's lensing. So what happened with our curious two Schwarzschild rod black hole solution? So what we ended up seeing is this effects in here. They imitate very well the dynamical problem, as I will see later. It's just that between the two lines, the lensing effect, not the shadow. The shadows are perfectly fine, and we tested that with a postdoc and one of the other faculty members in Portugal. The shadows are perfectly smooth everywhere. The It's just the jump here between these two black holes. So this is one of the proxies I wanted to show you. And I'm not going to show you a lot more of the equations, but I wanted to also say that we can place the observer everywhere within this models. And here we placed it directly when we sort of had the observer and was seeing the two black holes in a plane orthogonal, say, of where they're lying. We could have done that in another plane in which you have one black hole and the other one is kind of superimposed between the light that is coming from the background. And you would see this distortion on the left. This is what happens when you have those black holes and what you see with the shadows, which here on the right, this is some images that where it came up from NASA's simulations. You don't really can tell here what is the primary image, but they would start becoming these images in here. And it seems that general relativity is sort of consistent with this way of proxying, so to say, the full dynamical problem. Advantage is time. I can run this in 15 minutes on my laptop. I just need some Python ray tracing and I get the analytical solution, so I can choose any values of masses. If you do this, perhaps you would need a day to do so. Now, we know life is dynamical, as we can all experience. So what happened? Can we use these proxies to make a dynamical system? And what we argued is that yes, what we did in that case is not to move the system will still be static. It's just now the observer, the camera that is making the observations will rotate. And we can do that by doing a boost rotation analytically and emulating that and tracing back that movement, yes, with the effect of slowly moving the camera, which is equivalent, right, as moving the system as co-rotating. So we did that, and not because I tell you so, it's just, let me move into here. This is what we constructed. There's a small video that we had. There's a galaxy behind it, and this is our proxies for that approximation.
1 minute, please conclude.
Sure, of that dynamical system. So here's a comparison with a full dynamical system. And this is our quasi-static binary black hole emulation of the shadows. And so we can also, the last thing I want to show you is we can go to very high, extremely rotating black holes. We can have two Kerr black holes that are very close to each other, and they show very interesting shadows.
30 seconds.
I know numerically you can do that, but they will look like a Xinjiang, and these are exact shadows that we constructed. So that's everything I want to say. And the fun has just begun as we are learning today in the workshop. Thank you.
Thank you. Yeah, do we have any questions in the room? Yeah, so I was just really curious. Well, first of all, thanks for attending. It's wonderful to have someone close by in the region. So my question is really one of why is it that a, say, dynamical space-time solution where you're given the metric at any given point sort of numerically, is there any sort of fundamental reason why that would be so much slower than computing all the necessary sines and cosines and all that fun stuff associated with superposed Kerr metrics or superposed Schwarzschild metrics?
The superposed Kerr black holes are not two separate solutions. They're really self-interacting. So it's a one solution that has those features. And this is faster because we are really not doing the dynamical system. So we don't need any clusters or anything in doing that. And we can change the masses and the spins of the black holes to arbitrary values within the ones that are valid for the metric.
I see. And this is using the fast light approximation?
Yes. Mm-hmm.
Gotcha.